we wrote a small Python program to implement this very simple neural network. We assumed some random number, some random values for the weights w, and we used the sigmoid function as the nonlinear function, f that converts all the logits into the corresponding neural outputs, right? Converting the logits those z's, into the corresponding y's, right? The corresponding y's. So for our example, with the input x1 equals to 12.5 and x2 equals to 4, we saw that the outputs of our Python program were very different from the actual number of views and likes, right? And the reason that the outputs of our Python program were very bad is because the assumed weights were completely random. The neural network has not been trained using those examples. So in order to actually improve the performance of our neural network gradually, we need to build a feedback mechanism that can convert the errors in the outputs into corrections to those weights. We cannot just keep using this random number. We have to sort of start with some kind of random number and then make small corrections to the started value every time we sort of see some examples, right? So in order to build such a feedback mechanism, the first thing we need to do is to actually quantify the errors in the output, right? We need to actually come up with some numbers to represent how different our neural network's output and the actual number of views and likes per week, the actual outputs, right? So for our example, our output has just two numbers, right? It's the number of views per week and the number of likes per week, right? So we can set up this coordinated system with the number of views as the horizontal axis and the number of likes as the vertical axis, right? On this coordinate system, every output is just one point. Right? The output generated by our neural network is at the blue point, with its coordinates given by y12, y21, y21 and y22. Right? The horizontal and vertical axis are given by y21 and y22. Right? And then if we denote the actual number of views and likes per week for the same video as T1, and T2, T means ground truth. So T here means truth, true number of views and true number of likes, right? So this red dot, this red point, just represents the actual number of views and likes for the same video, right? And then once we have these 2 points, we can compute the Euclidean distance between the blue point and the red point, right? And the distance can be computed using this equation. So d is the distance equals to the square root t1, that's t1, subtract y21, that's y21. That gives you the distance along the horizontal axis, right? That's this blue line. That's the length of this blue line, right? And then t2 subtract y22. So t2 is here, y22 is here. So if you subtract them, that gives you the length of this segment, right? And this length is identical to the length of this green line, right? And then the distance can be computed using the Pythagorean theorem, right? It's using the Pythagorean theorem. So because this is a right angle triangle, right? If we look at this particular green triangle here, it is a right angle triangle, right? This line is parallel to the horizontal axis, and this line is parallel to the vertical axis, and this horizontal axis and vertical axis are sort of perpendicular to each other. So this is a right angle triangle, right? And then the length of the longest side squared equals to the summation of the length of the other two sides squared, right? And the length of this side is just the T1 subtract the Y21, and the length of this side is just T2 subtract the Y22, right? Just square those lengths and then add them together, then take the square root, we get the distance, right? That's the Euclidean distance. In practice, there are different ways for computing this kind of a distance, right? You don't really have to use this kind of a Euclidean distance. You can use other definitions of distance, right? The concept of distance can be generalized to account for different kinds of situations or different kinds of definitions, right? Suppose T1 and the two axes has very different scale. For example, the number of likes might be a lot less than the number of views, right? So the vertical scale could be sort of a lot smaller than the horizontal scale, right? So in that case, do you want to sort of multiply a certain constant to the vertical axis in order to actually make the two axes have about the same scale, that kind of thing? And also, this is some kind of, you have to take the square, right? Take the square and then take the square root. Sometimes you might want to use the so-called L1 norm, right? Those are issues that we will discuss in separate videos, and we will not get into those issues right now. So we can use this distance as some kind of measure as the error in the output of our neural network, right? And in practice, we're not really using the distance directly because you have a square root in the distance expression that gives that makes the calculations, following calculations, slightly more complicated, right? So in practice, what we are actually using is actually the distance squared. It's actually the squared distance, and then multiply by 1/2, right? So that's the error that we're actually using in practice. So it looks like this kind of thing. For this particular simple example, it looks like this kind of thing: 1/2, and then the distance squared. So this thing here in the square bracket is just the distance here squared, right? So so that's our quantification of the error, right? It's based on the Euclidean distance. So if the distance is very large, which means that our error is very large, right? If the distance is very small, so blue dot and red dot are sort of very close by, then which means the error is very small, right? And if the blue dot and the red dot coincides with each other, they are located at exactly the same location, then we have no error, zero error, that kind of thing, right? So so that's our quantification of the error, right? So now let's try to we have an expression for the error now. Let's try to take a closer look at what this expression actually means. Right? So here T1 and T2 are basically ground truth, right? They are given, so they are fixed numbers. In our example, T1 equals to 10, right? T2 equals to 1. So those are numbers that's fixed, right? Those are constants. Right? And then Y21 and Y22 are outputs generated by our neural network, right? So let's take a closer look at what Y21 actually is. What Y21 actually is, right? We know that Y21 is computed from the logit Z21 by applying the nonlinear sigmoid function, right? If you don't exactly remember how this thing is organized, this is the Y21. Y21 is the neuron output from this particular neuron, right? And then for this particular neuron, the logit is Z21. So by applying the sigmoid function on Z21, we got Y21, right? So Y21 was obtained by applying the sigmoid function f on the logit Z21, right? And the logit Z21 is just a summation of the outputs from the neurons in the layer beneath, which is layer 1, multiplied with the corresponding weights, right? If you so don't exactly remember, Z21, you have like 3 arrows pointing into this particular neuron, right? And for this one, it's a constant y10, right? And then the input along this particular connection is y11, right? And then the input along this connection is y12, right? So Z12 is just a weighted summation of these 3 inputs, with the weights given by these 3 weights, right? So Z21 actually equals to this particular summation. So this green box can be sort of expressed by the terms inside this green box, right? So Y01 is just a 1, right? So it's just a 1 multiplying W201. So W201 here, right? And then W211 multiply Y11, right? Y11 is what? Y11 is the neuron output from this particular neuron, right? And Y11 was computed by applying the sigmoid function to Z11, the logit Z11, right? So Y11 can be actually replaced with FZ11, applying the sigmoid function on Z11, right? So the stuff that's inside of this red box can be replaced by the stuff that's inside of this red box. That's applying F on Z11, right? You can do the same thing for Y21 here, because Y21 is just obtained by applying the sigmoid function onto not Y21, Y12. Y12 was obtained by applying the sigmoid function on Z12, right? The same process here, right? So, and then F is the sigmoid function, right? And then Z11 is just the logit of Z11 is just the logit of this particular neuron, and it can be computed by the linear combination of these 3 inputs, x1, x2, and x0, right? With the weights given by these 3 numbers, right? Right. So Z11 has this particular expression, right? And you can do the same thing for Z12 here. So Z12 can be expressed like that, right? So both equations are both terms can be actually represented by using the inputs and the weights, right? The inputs x1 and x2, x1 and x2 here are also fixed numbers. So in our example, x1 equals to 12.5 and x2 equals to 4. So those are just the constants. They are just the fixed numbers, right? So if we look at this expression for y21, the form of the nonlinear function f, the sigmoid function, is given. So it has a fixed form, right? x1 and x2 are given. Those are constants. So eventually y21 is just a function of the 12 weights, the 12 w's, right? If we do the same analysis for y22, we will also find that y22 is also a function of the 12 weights, the 12 w's, right? And because t1 and t2 are constants, they are fixed values also. So eventually, the error E is a function of the 12 weights, right? It has no other dependence. E only depends upon the 12 weights. And at the starting point, we assign random values to the 12 weights. So E could be very large, right? So E only depends upon the 12 weights. It has no other dependence, right? So our goal is what? Our goal is to find the correct set of values for the 12 weights so that the error E is as small as possible, right? The problem seems quite difficult. We have 12 independent variables for like one dependent variable, right? So it looks like it's 12-dimensional problem, it seems very, very difficult, right? But let's think about a simpler problem, right? Let's think about a simpler problem. In this simpler problem, the error term E only depends upon a single weight W, right? And the dependence here is very simple. The dependence E equals to W subtract 1, and then the whole thing is squared. And W is just a single weight, right? And we can actually make a plot of this relation, right? The plot is just a second order curve, right? So the vertical axis is E, the error. The horizontal axis is our single weight W, just one weight for us, right? And this curve actually has its minimum located at W equals to 1, right? When W equals to 1, E equals to 0. But if W equals to anything that's not 1, then W is going to be larger than 0, right? And for this very simple relation, we can compute the derivative of E with respect to W very simply, right? So dE with respect to dW equals to just 2 times W subtract 1, right? So that's the derivative, right? So for this very simple relation, the derivative can be computed very easily, right? For our simple neural network, this dependence, we can also write down the dependence, right? But it's going to be extremely complex with sigmoid functions and those linear combinations, right? We can also write down this expression explicitly, but the expression is going to be very, very long, and it's going to be difficult to understand, right? But here we have a very simple relation and just a one weight. But let's see how we can actually solve this very simple problem, right? Very simple problem. So the derivative is what? The derivative is what? The derivative is basically how fast the error term E increases with W at a certain point on this curve, right? So at W equals to 1, the derivative is 0, right? Which means at this particular location, right, if you change W a little bit, the error doesn't change, right? But if you actually at this particular point, right, if you change W a little bit, you could get a very large derivative, which means how fast the error actually changes, right? It's actually, if you want to be precise, it's actually how fast the E increases with W, right? But we don't want to increase E, right? We want to decrease E. So if we actually reverse the direction of the derivative at a certain point, we get the fastest decrease in E at that point. So if we take some small steps, along the negative derivative, we can gradually reduce E by successively modifying W, right? We change W a little bit at every step, right? So maybe we start from this point. This point is not the point that can actually make E smallest, right? This is the point that makes E smallest. But suppose we don't really know where the minimum actually is. We don't really know, right? In practice, we really don't know actually. We can just start from some arbitrary location that's given by random numbers, right? And then, if we can compute the derivative of E with respect to W at that starting point, we can just reverse the direction of the derivative by adding a minus sign, multiplying a minus 1, right? Derivative tells us the fastest increasing direction of the error, right? But if we reverse that direction by multiplying minus 1, we get the fastest decrease in the error at that particular location, right? So once we get that direction, we just go a small step along that direction, right? And then we can get some reduction in the area, right? And then we recompute the derivative again at the new location, reverse the sign, and then we go a little bit further, right? Take another small step. Then E is reduced even further, right? We just repeat doing this thing by many steps. Eventually, we can get to this location, right? And for this particular form of the function, it doesn't really matter where we start. We can start from this side, we can start from this side, we can start from very close to the minimum or very far from the minimum. It doesn't really matter where we start. Eventually, if we sort of take this kind of strategy, right, to go along the negative direction of the derivative, then no matter where we are starting, eventually we will come to this minimum point, right? So that's sort of the conceptual idea, right? So can we actually write a small Python program to implement our idea, right? Suppose we so let's look at the Python program. Can we actually do that? Can we actually do that? The program is actually simpler than you think, right? And again, it's actually quite close to English, so I will try to sort of explain the meaning of the code, but without getting into the syntax too much. Right? The syntax will be left for other videos. So suppose here we are again importing some libraries from pre-existing libraries, right? We're importing programs from pre-existing libraries. So here w underscore cur means the current value of w, right? We are starting with a w value that's -2. So on this particular graph, -2 is about here. So we are actually basically starting from a position that's like way above here. Right? It's kind of very far from the optimal, right? But it doesn't matter. Doesn't really matter. Right? In practice, you probably don't even know which value to start with. You can just pick a random number, right? In practice, it's given by a random number. That's your starting value. That's the starting weight that you start, the value that you started with. And then we have a variable that's called a learn underscore rate. Right? It's called a learning rate. Learning rate. Later on, when we actually get into the terminologies of deep learning, this is something that's called a hyperparameter. It's a number that actually controls how fast your neural network learns, right? In our simple example, this basically just controls this number, this variable, which is set at 0.01 here, actually controls how fast we want to go along the negative derivative. It's going to control the speed of the descent, actually, right? And then it's a constant, right? It's a constant. We're using a constant here, so we are not really modifying the learning rate along the trajectory. Yeah. So it's just a fixed number. Right? Then the variable precision, which has a very small value, a small fixed value, right? This value actually controls how accurate we want our result to be. So here we know the exact value is 1, right? But when it actually comes to a computer implementation, there's always a machine precision, sort of that kind of thing, right? So how precise we want our result to be is controlled by this number. So if this number is smaller, then it's going to be sort of very close to the real optimal. But if the precision is not so high, say 0.1, right? 0.1 instead of this 0.001. If it's not so high, then once the current value of w is close enough to this optimal, to the true optimal, then the program is going to stop and just return that value that's sort of close enough according to this given precision, right? And then step size is used to actually store the difference between two successive w values. So we are modifying w gradually, successively, right? So there's some kind of difference between the current value and the previous value. And step size is used to store the difference. and we're just initializing it with some random value 1 here. So, right. And then here we have defined a function to compute the derivative of E with respect to W. And this function takes an input W, right? So at every different W, it's gonna have a different derivative. So we need to compute the derivative, right? According to this particular formula, mathematical formula, right? We call this function dE dW, and it's gonna return the derivative at a particular W value, right? And this return value is exactly the same here, 2 multiplied W subtract 1, right? And now we can write a loop. Right, we can write a loop, and this loop will keep iterating when this condition is true. So when step size, which started with a value of 1, is larger than the precision, which started with, which is fixed at this very small value, then these 4 lines of the code is gonna keep iterating. So on the first line inside the loop, we are basically just assigning the current W value to a variable that's called W pref. So we can actually have a record of the W value before we actually make any changes to the W value, right? So W pref is just used to store the W value before it is being changed. And on the second line here, inside the loop, we actually change the current W value. We change it by adding this term to the current value of W, right? And this term is what? This term is the product of the learning rate that has a fixed value 0.01 here with the derivative of the W at W pref, right? So it's so learn rate. So if you actually move the W minus sign onto the derivative, that's exactly the negative derivative, right? It's learn rate multiplying the negative derivative, basically, right? So we are basically taking one step along the negative derivative, right? And for some reason, I sort of messed up the. Did I change anything in this code? Okay, so it looks like I didn't change this code by accident. So, and then on the third line, we just print out the modified value for the W, right? So here we have made the change to the W, and now we just want to print out the changed W onto the screen, so we can actually see what the change is, right? And then on the last line, on the fourth line inside the loop, we just update the step size. I was saying that the step size is used to store the differences between the two successive W numbers, right? And the step size equals to the absolute value of the current W value subtract the previous W value, and the previous W value is assigned here, right? It's a record that we have actually stored before we actually change to the current W value, right? So if we look at this particular loop, right? The learn rate is a fixed value, right? It's a 0.01. This value doesn't change inside the loop. It's a fixed value, right? But the absolute value of the derivative dE over dW, the absolute value of dE over dW actually changes, right? It actually reduces, right? As we actually move along this kind of direction, dE over dW is going to become the absolute value of it. It's going to become smaller and smaller, right? Because at the optimal point, dE over dW is exactly 0, right? As we get closer to the optimal, dE over dW is going to become smaller and smaller, right? So the size of this particular change the absolute value of this particular change that we have applied to the current value of W is going to get smaller and smaller as we get closer and closer to the optimal value, right? So as this change gets smaller, the difference between the current value and the previous value is going to become smaller and smaller, right? So step size is going to become smaller with iteration, right? And eventually, when step size is reduced to a number that's below the precision, the iteration is going to stop. This loop is going to stop, right? So we're going to sort of come out of the loop. And then after the loop, we will just print out the minimum value that we have found. And now let's run this code. Let's give it a run and see what's going to happen, right? This time I'm not going to invoke the. I'm still going to use the interpreter to run this code. It's called .py. So the code has finished running, so it's pretty quick, right? The minimum located at 1.0000, right? So we can sort of see the final result is correct, right? That's consistent with our visual inspection, right? And and during every iteration, it's going to print out the current W value, right? If we look at how W value actually changes through iterations, let's come to the top of the. So here we have executed this code. So W is started with a value of -2, right? That's the value that we assigned at the beginning of the code, right? And then this is actually after the first iteration. So W has become -1.94, right? -2 is over there, and then after one iteration, it becomes -1.94. So it's actually moving in the correct direction, right? And then after the second iteration, W becomes -1.8812, right? So as more iterations are carried out, W gets closer and closer to the correct value, right? So here it has come close to 0 now. W has come to this point here. Come very close to this point, right? And then it's gonna keep increasing, right? And eventually it's gonna come to 1, right? And one thing that we can notice is that the amount of changes between two successive W values is become smaller and smaller, right? So at the beginning, at the earlier iterations, the changes among two successive W values is quite big, right? You can actually visually see them, right? Later on, it becomes very hard to detect, right? The reason that you see no changes is because the significant number of digits, right? The changes is happening at very far along the after the decimal point, right? So it's not printed out. It looks like they are the same, but there are very small changes that's being sort of truncated during the printing stage. But in the calculation stage, those small changes are carried out actually. And this is for this particular very simple case, right? With just the one weight and this very simple dependence. What about two weights? Right? What about two weights? Suppose we have like two weights. So the error depends upon two weights, W1 and W2. Again, let's assume that the error E and the two weights W1 and W2 have this simple relation, right? It equals W1 subtract 1 squared plus W2 subtract 2 squared. Right? We can plot E as a function of W1 and W2. So here are the two horizontal axes. The two horizontal axes is W1 and W2. And then the vertical axis is the area E. So E is actually a surface, right? It's a surface instead of a line anymore. It's not a line anymore, it's a surface, right? Because we have two independent variables now, so we need to use partial derivatives. So both partial derivatives with respect to W1 and W2 can be easily computed for this very simple example, right? So partial E partial W1 is just 2 times W1 subtract 1, right? And then partial E partial W2 is 2 times W2 subtract 2, right? So the partial derivatives can be computed without too much of a difficulty. So now let's look at the Python program that allow us to find the best values for the two weights, right? The best value for the two weights is what? W1 equals to 1 and W2 equals to 2, right? When W1 equals to 1 and W2 equals to 2, E equals to 0. If W1 and W2 deviates from the optimal value, then E is going to be larger than 0, right? So for this very simple example, we know what's actually the true optimal values for W1 and W2, right? Now let's look at this two-dimensional case, right? This two-dimensional case, and it's given by this particular Python program, right? This Python program. Some part of it is going out of the screen, so let me move it over, right? So this piece of code, it looks remarkably similar to the one-dimensional case. Pretty much the same, actually, right? The starting value for the weights is not a single number anymore, right? It's actually two numbers now, right? It's not a one value, it's two values because we got two weights. So W current has two values in it, right? So the first value is the starting value for W1, and the second value is the starting value for W2, right? Again, they can be replaced with some random number, but here I'm just sticking some arbitrary number into it, right? And the other three variables are pretty much the same. It's even the values are the same, right? I didn't actually change anything for the learn rate, precision, and the step size, right? The function for computing the derivatives has been changed, right? Because now it's not just the one derivative that we need to return. We need to return two partial derivatives, right? So the return statement in this function has two values in it. The first value is for the partial derivative with respect to W1. So it should be equal to 2 times W1 subtract 1, right? So 2 times, so W0, W is the input, right? W0 corresponds to W1 actually here. And then the second derivative is 2 times W2 subtract 2. So here it's 2 times W square bracket 1 subtract 2, right? W square bracket 1 is equivalent to W2 here, right? It's actually a direct translation of the mathematical formula, right? The structure of the loop is still the same. The structure of the loop is still the same. So here I'm storing the output from the derivative computing function into a separate variable that's called D, right? So D is gonna have two numbers in it. It's a container with two numbers in it, and the first number is actually the partial derivative with respect to W1, and then the second number is gonna be the partial derivative with respect to W2, right? And then we then update the first weight W1 using the first partial derivative D0 and multiplying the learn rate. Again, don't forget the minus sign, right? It has to go along the negative derivative, right? It cannot go along the positive derivative if you want to sort of reduce the error, right? And then the second weight, W curl 1, that's the second weight, is updated using minus the learn rate multiplying the second value in the D container, right? The second partial derivative. And then the formula for computing the step size has been changed, right? Here, if we are just in one dimension, the difference can be just computed by subtraction and then take the absolute value, right? But here we are actually in two-dimension space, so every W has two numbers in it, right? So the current W and the previous W, both of them have two numbers. So in order to actually compute the step size, we actually have to actually compute the Euclidean distance between those 2 vectors, basically, right? So it's the current this is the current W1. This is the previous W1, right? And then we are squaring it by using the power function, and then add. This is the W2 current W2. This is the previous W2, and squaring it, right? And then we add these two squares together, and then take the square root. That's our step size, right? And everything else is identical. So again, let's run this particular program and see what's going to happen. So the minimum is located at 0.99999. That's close enough to 1. Right? We know W1 has the optimal value of 1, right? And this is 2.000 something, right? This is the optimal value for W2, and we know that the optimal value for W2 is actually located at 2, right? So if you actually sort of accounting for the machine precision and also the precision that we used for sort of stopping the iteration, then this is actually close enough to the true optimal values, right? So for our neural network, we have 12 weights, right? It's not one weight, it's not 2 weights, it's actually 12 weights. It looks a lot more complicated, but the same idea still applies. So all we need to do is to actually find the partial derivatives of the error with respect to the 12 weights, right? And then we can just adapt our simple Python program, to gradually modify the values of the 12 weights to reach the minimum error. And the difficulty is in terms of writing this derivative function. So for 12 weights of our neural network, how do we actually write the derivative function, right?